Hello everyone. So we've been looking at public key cryptography and how to use number theory to accomplish it. And we already saw how to do public key encryption, asymmetric encryption, where the receiver has a secret key that's not shared with the sender. And encryption is done under a public key, which was already quite cool. It turns out that when public key crypto was first realized through RSA, what they thought was even more interesting and significant was the ability to do digital signatures. And that has turned out to be a technology of widespread use nowadays. So this is the primitive we're going to start looking at now. Let's go back to seeing what signing represents for us usually in the non-electronic world. It's captured by handwritten signatures, which we all know well. One example of this is when you sign a check. How is that supposed to work? Well, Alice, say, makes out a check to pay Bob $100, and she affixes at the bottom her handwritten signature. What's supposed to happen after that is Alice will give the check to Bob, who will go to his bank and submit it. Bob's bank will then somehow be in touch with Alice's bank to clear the check. When that happens, Alice's bank will check that the signature at the bottom is really hers. They can do that because they have on file a prior copy of Alice's signature, and they perform some comparison. And if that comparison works out, they say the check is valid and Bob gets paid, otherwise it's not. Now, of course, this type of clearing is a little dated. I think nowadays banks don't even verify signatures unless the amount is above a certain something. Maybe you're expected to complain when you get the return check or whatever, but this is kind of the way things are supposed to work. If you try to lift that to an electronic setting in the most obvious way, what you might do is have Alice sign and give her handwritten signature on a piece of paper, and then just turn that into an electronic format. Take a photo of it or scan it and turn it into a JPEG file. And at that point, it's just a bunch of bits. And you can attach those bits to any document that's sent out. So when Alice sends out a check, she just, as an attachment, includes this file. And then the rest is the same. You do assume that the entity performing the verification has some sort of copy that they can compare. But there's a significant difference in terms of security between this and what we have in the real world as handwritten signatures. The problem is that once you turn that handwritten signatures into a file or bits that are sent across the internet, it's very easily copied. So anybody can simply detach that signature from whatever Alice attached it to. And once they have it, they can attach it to anything else and forge Alice's signatures at will. This is not so easy with a handwritten signature, because if you are yourself going to be handwriting, you have to kind of copy Alice's signature. And the presumed difficulty of doing that is what underlies the security of handwritten signatures in the real world. Furthermore, this just the fact we see here yields a kind of interesting conclusion about signatures. Namely, nothing which is just a token or object attached to the data can possibly function as a signature, because you can always detach it and put it on some other data. What that says is signatures actually have to depend on the message. Every time you have a different message, you better have a different signature that only Alice can compute. That is not at all our perspective with handwritten signatures. Despite this being how we see signatures electronically now, it turns out that a lot of the way signing is done today and electronically is effectively by some kind of digital rendition of handwritten signatures, which obviously has issues. So, and we do this all the time. So I do it, for example. So here's an example. So signing of Adobe documents. So every year I have the privilege of writing nice recommendation letters for people who have taken 107 and go on to grad school. So here's someone who not only took my undergrad class, but even took my grad class after taking the undergrad class and aced it. And when I write a letter of recommendation like this, I'm expected here to put a signature. So how do I do that? Well, if I go into Adobe, there's a place where earlier I have simply drawn with the mouse my signature, and I can now attach it and put it here. And then I can save the file and send it off. And as we just saw, security-wise, this is a little questionable because this thing that I put here on examination of the PDF document here could be extracted and put onto something else. But we don't seem to worry about that too much. In any case, back to our story. Before we start developing new technology for digital signatures, one might wonder, why is the problem not solved by a message authentication code? Remember, that was the primitive which gave us authenticity and integrity in the symmetric setting, where parties who are generating and verifying the tags share a key between them. That could work here. What we would do is that Alice, when she wants to sign, would run the entire message through a MAC algorithm, say HMAC or encrypted CBC MAC or whatever. That works under the influence of a key K that she has to get a tag. And then when she sends the check to the bank, she attaches the tag. The bank will verify this using the fact that it's also in possession of the same key. It needs that to check. Digital signatures have some attributes beyond MACs that make them interesting. One of the issues here is that since the bank has your key, the bank can actually forge your signatures. You might say, okay, well, we trust the bank for various reasons, possibly, possibly not. But the further question is, do you trust their servers? Do you trust them to store your key securely? Do you trust that even if the bank's policy is not to use your key maliciously, that every employee there is honest and you don't have some kind of insider attack? So there are many reasons for which people would like that the entities verifying signatures are not able to themselves generate signatures. And that's the asymmetry that a digital signature provides. So the bank will not be able to forge signatures, and indeed the verifier of a signature does not need to share a key with the entity who generated it. And indeed verification doesn't require knowing any secrets. So as with any crypto primitive, we start with some syntax. So we need to say, if you're going to specify a digital signature scheme, what do you actually have to specify? And just as many other objects we've seen, encryption schemes and so forth, are tuples of algorithms, this is two, and there'll be three of them: key generation, signing, and verifying. The key generation algorithm, just like for asymmetric encryption, produces two mathematically related keys. The entity running it is the one who wants to generate signatures. She gives this box a kick, it'll provide a secret key that she stores, and it'll supply a public key that will be used for verification. And we now assume that somehow this public key winds its way to whoever is going to verify the signatures that Alice generates. If Alice wants to sign a message M, she runs it through the signing algorithm with the secret key to get as output sigma, that's the signature, and that's sent across the transmission medium together with the message in the clear. Again, we're trying to get only integrity, so data is in fact sent in the clear. The adversary here will be wanting to tamper with the data, but to make the verification succeed, it has to also somehow update the signature to match. Whatever it does, the verification algorithm is able to take a candidate message signature pair and somehow check that they match up. And it'll return 0 or 1, indicating which of those it thinks is true. And this is what would be run, say, by the bank or whoever in our application. As usual, to be clear, the syntax is not telling us any specific method for implementing these algorithms or how they work. It's just giving us the framework. These are the objects you want, and we'll have to find some math to actually implement them. So far, we also have not talked about security, although we will, but we, as usual, have to have some correctness requirement just to make sure that communication is correct. What that means here is that if you have a pair of keys pk and sk generated correctly through k, and if you sign some message m and you give the verifier the public key message and that signature, that verification will always succeed. It says with probability 1 because there's a probability distribution over keys generated by this, potentially over signatures, and so forth. Now, how are we supposed to set up a signing system? The way we imagine it works is that Alice starts by running some key generation algorithm on her local machine and gets a pair of mathematically related keys, the public and secret ones. She stores the secret key somehow securely, and then in the next step, finds a way to disseminate the public key so that any verifier gets it. We've seen many systems which generate keys, RSA, Diffie-Hellman systems. They all come with algorithms. These algorithms are widely available. You can download OpenSSL and run them. So anybody can start generating keys if they feel like it. This step does involve some thought and issues. For the moment, we're going to assume it's magical, that Alice somehow manages to communicate the key, public key, to the verifier. Once all this is done, Alice can start signing. She uses now the signing algorithm of the scheme to generate signatures on documents of her choice with her secret key. And if those documents and the signature reach anyone, Bob holding the public key, they can verify the signature. So the step there, as I briefly indicated, that's a little difficult is how do you properly disseminate that public key? The fact that we call it public means it's okay for anyone to know it and see it, but that doesn't mean that there are no security concerns attached to it. The verifier needs to be assured when it has this key that is supposed to be Alice's public key, that it's really hers and not someone else's. Clearly, because you're trying to verify Alice's signature, not someone else's. There are various ways you could do that. You could put the key on some public place, maybe your Facebook or your web page. You could include it as an email attachment and so forth. And the most common, for at least for web servers, is to use certificates. And we'll discuss that later, partly because certificates actually themselves employ digital signatures. So there's a little interesting circularity there. We turn now to defining security. Before we can give any examples of such schemes, we need to know what our goal is in that regard. This is easy because we've already studied message authentication codes. That's what I mean by these message authentication schemes. And we gave a definition of security, UFCMA, and forgeability under chosen message attack. And not much is required to change to move that to the asymmetric setting of digital signatures. The only difference is that the public key is present, and that'll simply be something the adversary gets. So roughly the idea is that the adversary is going to try to get a verifier to accept something as Alice's signature on some message, even though Alice never really signed that message. In this process, the adversary can pick any message it wants as long as Alice hasn't actually signed it in the past. If this adversary can get someone to accept something as Alice's signature of it, the adversary wins. But additionally, the adversary has the ability to see Alice's signatures on messages other than the one on which it is trying to generate a forgery. Furthermore, it can even choose these messages. So that's kind of the couple of lines rendition of the definition, which is hopefully somewhat familiar since you've seen it before. And here are the games. We've by now seen tons of these, so hopefully quite simple to work through. So we fix a digital signature scheme. That just means we are given and know these three public algorithms. We haven't seen any example of such a scheme yet, so that's coming. A is the adversary, and here's the game associated to the scheme, which appears as a subscript. The game starts with initialize, which does the same thing as you would expect for public key encryption, which is that it runs key generation, it gets a public and secret key pair, and what it returns is the public key. It does not, of course, return the secret key. There'd be no security left if it did. It also initializes a set to 0 for bookkeeping. Now the adversary will get this public key as input. To see what the adversary is trying to do to win, it's most helpful to first go here. The adversary is going to trundle along and eventually output a message and some claimed signature of it. The game will take those and it'll verify them. It'll run this verification algorithm with this public key and the adversary provided message and signature. And winning is very simple. As long as the adversary's provided signature is correct, meaning this bit is a 1, then that's it. Your adversary has won. It's managed to create a message and a correct signature for it. And Alice never sent that message, so it wins. Okay, but if that wasn't enough, the adversary has further power. In a real usage of this, you would expect that Alice is generating signatures on some messages. It would every now and then sign something, and we assume the adversary can see that. Even more, the adversary can go to Alice and say, hey, here's this message M. I'd really like you to sign that, because if I see the signature of that, I can break your scheme. And for some reason, Alice is happy to oblige. She will take this message M, she runs the signing algorithm on it with her secret key to get a signature, possibly randomized, but often not, and returns that signature. And then the adversary says, okay, that's cool, but now I want to see the signature of another message. So it provides another query to this oracle and gets another signature. So after a while, the adversary accumulates all these signatures, and then it tries to output an M and sigma, which allow it to win. Now, of course, there's a trivial way to win. This adversary could simply take a message it queried here, take the signature it got back, and output those. Of course, by the correctness condition, since they were correctly created by Alice, the correctness condition says D here will equal 1 and the adversary will win. But that isn't a real victory because that message was in fact signed by Alice. Alice agreed to sign it and it's an authentic message. So we add the condition here that messages are not allowed to belong to the set S, where S is everything that you've queried to this oracle. And so the intuition is pretty simple. Anything you have not requested a signature of is fair game to forge. When you run the adversary with this game, it may win it or not. Finalize returning true means it wins. That's an event which has a certain probability. That probability is the advantage of the adversary. Superscript stands for unforgeability under chosen message attack, the name of the metric. This means it's for this scheme, and this means it's for this adversary. Okay, so that is kind of the main theoretical concept here to understand, and now we'll start looking at different examples. Before we do that, here's a written summary of stuff I said verbally, so you can have it if you have a copy of the slides, but not the transcript. So remember that the return PK statement in initialize tells us that the adversary gets the public key as input. Of course, it doesn't get the secret key. It can call the sign oracle as often as it wants on any message of its choice. And winning can thus then be interpreted as follows. To win, two things must be true. The adversary provides a message and signature which is correct in the sense that verification succeeds, and new in the sense that it was not a query to sign. Remember that these games are mathematical abstractions. In real life, sign Oracle represents the signer Alice, and finalize represents the verifier or receiver Bob. But we don't have to have that inside our formalisms. Okay, so now we're ready to see how we might actually do this. It turns out that RSA lends itself very nicely and easily to signatures. And while when studying encryption, we started with discrete log-based schemes and moved to RSA, here we'll do the opposite. Remember that whenever we work with RSA, we start with an RSA generator. That's an algorithm that gives us all the parameters we need to set up the system. And remember that if you run it, it's a randomized algorithm and it'll return a modulus, two primes whose product is n, an encryption exponent and a decryption exponent, and all of these satisfy this whole bunch of mathematical conditions that we studied before. Almost always when you use RSA, you will set the modulus and encryption exponent to the public key and the secret key to the decryption exponent. Now, it's convenient to also throw the modulus into the secret key, even though, of course, it isn't actually secret. So the secret key actually looks like this. So here what we are saying is that for our RSA signature examples, I'm just going to fix key generation to look like this. And so that leaves me to describe how signing and verification as algorithms will work. RSA is, as we indicated, very naturally amenable to signing. And here's how you would do it. Remember, the signer has a secret key, which is a decryption exponent D, and the public key is the modulus and an encryption exponent E. When I want to sign a message Y, I think of the message as a point in Zn star, and I regard it from the point of view of RSA encryption as a ciphertext. And then I decrypt it. Having the secret key, I can raise it to the dth power, which is RSA decryption, to get X, and I return X as the signature. The idea is that someone who doesn't have the secret key cannot perform decryption, so it would not be able to decrypt this object here. Now, there's no message being encrypted here. It's rather that we're taking this message, this object now, the message to be signed, and letting it play the role of a ciphertext, and what comes out is called the signature. How do you verify? Well, verification is only allowed to have the public key. It doesn't have the D, so it can't take the message and raise it to the dth power and check that it gets back the claimed signature. Instead, given message Y and claimed signature X, it encrypts the signature by raising X to the E mod n and checks if it gets back Y. And if so, it returns 1, otherwise 0. And why does this work? Well, that's exactly the basic property of RSA. So RSA says that if you raise something to the E and then to the D, you get back what you started with. So if X is Y to the D, it must be that X to the E is Y. So correctness follows directly from the RSA property. This is indeed what RSA had suggested as how signatures should be done. And we can ask ourselves, what did they think about security in that case? Well, the way they thought about it is if you want to forge the signature of a message, call it Y, and you have the public key but not the secret key, you have to raise Y to the power D mod n, that's the signature. But that means you have to invert the RSA function at point Y. And if you remember, RSA is one way, at least for properly chosen parameters. We spent a lot of time studying and justifying this, still of course an assumption, but that as long as you can't factor this modulus, it will be difficult to compute Y to the power D. Okay, does that mean that the signature scheme is secure? And the answer is, of course not, because our metric of security is a lot more stringent. It's UFCMA. Whereas when RSA was developed, that was not the metric. Their metric was rather some sort of informal view like this. And when you come to look at it from the point of view of our definitions, there are very natural and obvious attacks. So here's one, this adversary here. So our intuition was that if I want to compute the signature of some message y, I have to raise y to the dth power. And oh, that's really hard because I don't know d, I can't factor n, and this function is one way. But remember, one-wayness is a property that holds when the points you have to invert are randomly chosen. But in a signature scheme, when you're trying to violate UFCMA, you get to pick the message. And so we notice something very simple. Set the message to 1. Well, what is the decryption of 1? I don't even care if I know what D is, because 1 to the D is always 1. So this says that 1 is a correct signature of 1. The message 1 has signature 1. And that's it. This attack just by itself shows that UFCMA does not hold for the prior scheme. By the way, if I didn't mention before, we call it plain RSA because we'll be evolving RSA further for signatures. And we're basically done as far as the security of plain RSA goes. Still, I'll give you a second attack. The purpose of that is to illustrate another attack vector, which is interesting because it exploits the algebra of the system. Algebra is kind of a double-edged sword. It's what makes RSA work, and yet the same mathematical properties will also give rise to weaknesses. So the property we exploit here is mathematically kind of obvious, but it gets interesting when you see it in terms of signatures. Suppose I have 2 points, y1 and y2. I multiply them mod n and raise the product to the dth power. Naturally, I get back this, the same as if I multiplied them separately. Right? Mathematically, it's entirely evident. Nothing really to say about it. But now, think about it in terms of signatures, and it's saying something much more interesting. It's saying that if y1 and y2 are messages, this is the signature of their product. The signature of the product messages is the product of the individual signatures of the individual messages. So that gives rise to an attack. In the UFCMA game, I can pick any 2 distinct messages, let's say that are different from 1. Remember, I have access to a sign oracle. I can go to it and get back a signature of x1 and of y1, call it x1, and a signature of y2, call it x2. Fine, now to win I have to create a forgery. That means I have to find some message and a correct signature of it. The only choices of message excluded are y1 and y2. If I output one of those, I'm not going to win. So I just use the product y1, y2. By this equation, its signature is just the product of these 2 signatures, so I can compute it. And again, by the same equation, this will work. So this adversary will win the game with probability 1. We may ask, why did we exclude 1? Because otherwise this pair might equal either y1 or y2, and then the adversary wouldn't win. So we've pretty convincingly broken plain RSA signatures. Now, historically, that's a fairly important lesson. One of the reasons is that when Diffie and Hellman introduced public key cryptography, they suggested that signatures are just the opposite of encryption, which is basically the paradigm we just saw. In other words, they said when you want to sign a message under some secret key, you treat the message as a ciphertext and decrypt. When you want to verify that what was generated here is a correct signature on a message M, you encrypt with the public key the signature and see that you get back the message. And you can see that that's effectively what we did in our RSA example. But as time went on, people realized that this has got quite a few deficiencies. In particular, it seems to think public key encryption is deterministic. So what they really mean in our language is what we call trapdoor permutations. But more importantly, it just doesn't work. RSA is an example where something like this fails. But nonetheless, if you look on the internet and some textbooks, you'll often find that they do kind of think of signatures as the reverse of encryption. There are other issues with plain RSA that we'd like to resolve beyond security. There's also the usability fact that in the plain RSA scheme, the message was assumed to be a group element in ZN star. But that's not what you want in practice. In practice, our messages are emails, files, videos, and so we would prefer to be able to sign strings of arbitrary length. Now, the evolution of digital signatures following these weaknesses being discovered in plain RSA was on two fronts. There was a big theoretical thrust which created a bunch of very clever schemes which were UFCMA secure, but not necessarily terribly practical for real-world use. What we're going to look at here is something that's what everybody does, and you can use that. It's just a slight modification to plain RSA, and it makes things work. And the idea is to use a hash function in addition to what we had before. So let's h be a hash function and assume its range is Zn star. Remember, the n here is part of the signer's public key, and the domain of the hash function is any strings. So let the secret key be n comma d. So that means the keys are just like the plain RSA scheme. And we call this the hash then decrypt scheme. So what does it do? Well, when it wants to sign a message m, it will again raise y to the dth power, except y now is no longer n. It's just its hash. So you can, in other words, look at it succinctly via this formula. We define the signature under secret key nd of message m to be created by take the hash of m, that gives you a point in Zn star, and raise it to the dth power mod n. That's it. That's our signature scheme. So the signing algorithm would then look like this. How do you verify? You check that if you encrypt the signature x to the e mod n, you get back not the message, but its hash. Since the hash function is public, the verifier can also create this y, and when it's given this candidate message signature pair, it can then do this check. So that's it. And it turns out that by and large, this is a very popular way to sign, and at some level, it's also good, but subject to properly doing the details. So let's turn to that part a little bit. What are the details? Well, one of them is, how do you choose your hash function? What hash function do you use? And here it's interesting to see that we're now going to come to what was effectively the killer app for collision resistance. We studied in the past hashing, and we talked about this CR, or collision resistance requirement, and kind of said that it's going to take us a while to come to the main reason we want this, but now we're here. So here's the observation. Suppose that we have an adversary that could find collisions for H. Remember what that means is it finds 2 points M1 and M2 such that the hash of M1 and M2 are the same, but M1 and M2 are different. So somehow this adversary finds a collision. We claim that if I have access to that adversary, I can easily violate UFCMA for the signature scheme. How do I do that? Well, I now write a UFCMA adversary. It gets input the public key, which for RSA is N and E, and it has access to a sign oracle, and it's going to try to output a forgery. It first leverages this given adversary to generate this pair of messages, and now it knows the hash of M1 equals the hash of M2. The observation is that if that happens, M1 and M2 have the same signatures. Why? Because the signature is the hash of the message to the dth power, and if the hashes are equal, so are the signatures. What that means is our adversary can go to its sign oracle, submit one of the two messages and get a signature. And then it outputs the other message and the same signature. This signature works for M2 by all these equations, but since M2 is not equal to M1, that is a victory for the adversary. So what we conclude from this is that A necessary requirement on the hash function is collision resistance. It better be hard to find two messages with the same hash. But that isn't necessarily enough. It's a necessary but not sufficient condition. To see a little bit about what other conditions might be involved, we can look at how RSA-based signing has been done in practice. So PKCS is a very well-known standard for RSA signatures. Modern standards mostly just use that. And what we see here is an older version of the standard. So what they did is that they, of course, were doing RSA signatures using this same basic hashed and decrypt paradigm. So the public key was modulus and encryption exponent, secret key modulus decryption exponent, and in this illustration, I'll assume a 1024-bit modulus. Now, the abstract scheme was written in terms of a hash function mapping strings to Zn star. But in practice, you're not handed something like that. What you instead have is something like SHA-1, which maps arbitrary length strings, roughly, to strings of length 160. So somehow they have to leverage that. So here's what they do. They hash the message with SHA-1, and that'll give them 160 bits, which is 20 bytes. That leaves them with a lot of room, because what they need in order to get a result in Zn star is a 1024-bit string or 128-byte string. So what do they do for the other, 108 bytes? They start with some constants here and continue with some other constants. So 0001 and all this. And that's it. This is the definition of the hash function. Now remember that the signature is the hash result to the dth power. That means this string is interpreted as an integer in Zn star, and then that's raised to the dth power. And okay, so that's it. That was the PKCS1 scheme. Now, as our understanding of signatures grew, we started to observe facts like this. This certainly creates something that you can implement, since this is a point in Zn star. But it has a lot of fixed bytes. Everything except 20 bytes is always the same. And that means that this hash function output doesn't look random. And that lack of randomness means that it doesn't mesh properly with our understanding of RSA. The reason we think this is secure is we think that this operation for an adversary is inverting RSA. But that's only true if the result of this is random. And this sure doesn't look random. So the change that's been largely understood to be appropriate is to not change the paradigm of the scheme. It's still hashed and decrypt, but you implement the hash function in such a way that the result of the hash changes, every bit of it changes whenever you change the message. So here's how you might do it. You take a good SHA function like SHA-512, and you apply it to the message. That'll give you back 512 bits. If you want more bits, you use this kind of strategy where you maybe prepend something here, then you change what you prepend and so forth. And this way you get a lot of bits out, and you can take out as many as you need, which is the length of the modulus, say 1024. When you implement hashing this way, you find that every time you change the message, everything changes. And so the result is much more random looking. And that's what's called full domain hash, and is a good way to do RSA-based signatures. So the takeaway then is that we have arrived quite simply and nicely at a quite solid way to do signatures with RSA. And the answer is full domain hash. If you need a scheme, you can consider that one. And it's remarkable that, that it was possible to do it like that. So here's an exercise where there's another RSA-based scheme, and you get to look at it and see that it isn't secure. Okay, so this asks you to present an adversary.